you'll see that our aim for today is that we are going to be able to graph linear inequalities in slope-intercept form. So this is a little bit different than what we've done before. At this point, we've graphed linear equations and not linear inequalities. So we're going to find out some things that are a little bit different about this today, just like when we were graphing inequalities that were just variable, like these examples here. So I've actually got some instructions that I want you all to do independently. Only should take you about 45 seconds. I want you to answer these 3 questions about these 2 graphs of single variable inequalities. Okay? Please go ahead and answer these 3 questions. What is the difference between the 2 inequalities? What does the difference mean? And I want you to write the inequality that each number line represents. Somebody with a raised hand, tell me, what is the difference between the 2 inequalities graphed at the left? This is the most basic question. A 5-year-old could probably answer it. Michael. Perfect. One has an open dot. One has a closed dot. All right, what does the difference mean? What does it mean about the solutions to these inequalities? Raisa. Okay. So she's telling me that it means that symbolically the open dot has a greater than or less than symbol, whereas the closed dot has greater than or equal to or less than or equal to. In terms of what does that mean for the solution itself? What does it mean about -3 in the solution to these inequalities? Rebecca. Okay, so I'm okay with Rice's answer. That's an excellent answer. That's what I saw in half the papers. The one I'm going to write down, not because it's any better, is that open dot is part of this inequality. Open dot is not part of the solution. Closed dot is part of the solution.
If the open dot is not part of the situation, if the open dot is not part of the situation, then why is it?
Excellent question. So Kendrick's trying to clarify here. If it's an open dot, it's not part of the solution, why even have a dot at all? It's because we need to recognize that everything that's so close to that -3 is part of the solution. -2.99999999999999999 part of the solution. Okay? So we want to make sure that it's clear that this is where we're starting and everything to the right of it is part of the solution. So we put a dot there to prove that that's where we're starting from, but that particular point itself is not quite part of the solution. Good clarification, Kendrick. All right. Let's look down at the next thing. We're going to keep those ideas in mind here in a second. What I want you to do is I want you to take the equation y equals 3x minus 5. I want you to graph 3 points of that equation. Once you are done graphing the 3 points of that equation, I appreciate those of you who are waiting to do this. Once you do that, I want you to take one, actually go ahead and take 2 of those points and plug it into this inequality. Once you do that, I want you to tell me whether the statements that you get after you plug them in are true or not. Okay? Graph 3 points, plug 2 of them in, tell me whether they are true statements or not. Okay? Okay, track back to me in 5, 4, 3, 2, and 1. Kip yes or Kip no. Are these two statements true? Kip yes or Kip no. Are these two statements true? Malcolm, why not?
Because -2 is greater than -2 is equal to
Yeah.
-2.
-2 is not greater than -2. It is equal to -2. So these statements are not true. So if I was to graph this inequality, y is greater than 3x minus 5, would I want to include these points as part of the solution? Kip yes or Kip no. Would I want to include these points that are on this line that we graphed as part of the solution? No. So that's very similar to when we run into this problem up here, where we have -3, like Kendrick pointed out. -3 is so very, very close to part of our solution. It's on the borderline, but it's not part of our solution. So we're going to find a way to graph this in such a way, graph these points that are on the borderline in such a way that we recognize them as on the borderline, but not part of the solution. The way that we're going to do that is we're going to come over here for graphing the solution. We're going to go ahead and graph those 3 points as we normally would. But since we have that open inequality symbol and we know these points are not part of the solution, instead of connecting them with a solid line, we're going to connect them with a dashed or dotted line. And so what does that dashed or dotted line signify to me about this line? Manuel? Those points are almost part of the solution, but they're not. Okay? We're going to talk a little bit more about the rest of the solution in a second. Let's come back down here. If we plug those same points into the inequality when it's greater than or equal to, are those statements true? So let's go ahead and plug them in.
Yes. Yes. No.
Thank you for waiting for the rest of your teammates to have an opportunity to get that worked out. Kip yes or Kip no. Are these statements true? Yes, absolutely. -2 is greater than or equal to -2. So now these statements are true. So when we graph this inequality and we come back to this and we want to graph the line for this inequality, again, I'm going to graph those same points. And this time, they are part of the solution. So I don't want to use a dotted line because the dashed line says this is not part of the solution. So I probably want to use a solid line. Now, the lines themselves are not the entirety of the solution. There's an infinite number of points along this line that are part of the solution. There's an infinite number of points along this line that are almost part of the solution. But then there's a whole bunch of other points. Think back to our do nows over the past couple days. Not today, but the 2 days before. I had you taking points and plugging them into an inequality to see if they were part of the solution. I actually want you to do the same thing now. each of you is going to pick some points. Your choice. Do not use the same points that I do. You're going to pick a point. I'm going to start with, actually no, I'm not going to do that. I'm going to start with this point here, 4, 2. And you're going to plug it into the inequality, and you're going to see if it works. So I'm using 4, 2. And I'm going to get 2 is greater than 3x times 4 minus 5. 2 is greater than 12 minus 5. 2 is greater than 7. Is 2 greater than 7? Keep yes or keep no. Is 2 greater than 7? No. So I'm actually going to have to erase this. And I'm going to have to choose another point. But you want to go through and you want to choose x, y pairs from this coordinate grid until you find 2 sets of points that are part of the solution. Okay? Does everybody understand what you're doing right now?
Yes.
Okay? You're picking points on this coordinate grid until you have found 2 that are part of the solution. Do not choose points on the line. Let me make that clear. You cannot choose points on the line. Because those are not part of the solution for this one, right? Because they're not equal to. You should already know that. So these are the points that we've all already proven are part of this. When we look at it, what do we recognize about all of the points? Where are they? Rebecca. They're all on the same side of the line. Now, if we go back through this and we were to pick a point here, 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 we would find that every one of those points is part of the solution. Because indeed, every point that is on the left side of this line is part of the solution. So, just like over here, we don't just choose a point and choose a point and choose a point. We shade the entire thing and then put the arrow onto it that says that it goes on forever. If we want to represent every solution to this inequality, we're going to do the same thing. Shade right over it. Everything on this side of the line is part of the solution. Even the numbers really, really close. I remember we chose this point right here. 2, 2. Really, really, really close to the line. But it's not on the line, so it is part of the solution. Okay? Same thing is going to go. If it's greater than or equal to, not only are all of these points along this line part of the solution, so is everything else over here.
Wait. So we shade the entire thing?
Everything to the left-hand side of this line. I moved over to the greater than or equal to. Everything on that side of the line is part of the solution.
Wait, but what about the other side? Because I'm confused.
So many of you probably plugged in some numbers that were over here on the right-hand sides of these equations, or right-hand sides of this line. Did those work? No. None of them on this side of our line should work. None of them. So we have the entire solution by graphing the line, determining whether the line is part of the solution or not, and then shading the side of the line that has the rest of the solution. Now, question is, how did we determine which side of the line to shade? What did you do? You guys did this already. How do we determine what side contains the rest of the solution? Katie? If it's close to the solution, so we have, if we look back up at our graph over here, There are points that are way, way out here that are part of the solution. They're not close to the line. On the other hand, there are also points that are really close to the line on the right-hand side that are not part of the solution. So closeness to the line didn't really help us decide. What did we do? We physically did something. You did something already to prove this. Javier.
Prove that the left side of the line is
By doing what? What did you do?
plugged into.
Yeah, you picked a point and you plugged it in. So we can always determine which side to shade by picking a point, not on the line, pick a point, not on the line, and plug it in. If the point you use works, it's part of the solution, then everything on that side of the line is part of the solution. If you plug in a point and nothing on that side of the line works, or excuse me, if you plug in a point and it doesn't work, then nothing on that side of the line will work, and everything on the other side will work. We'll see a couple of examples about how we can use this here in a second. But we're at this point, we can actually go ahead and fill in our key points for today. 2 key points about the difference between graphing equations and graphing inequalities. What's the first thing that we did that was different? Graphing inequalities. What was the first thing that we did that was different? I know that more than Manuel and Rebecca have their brains engaged today. So I need to see more hands. What is the first thing that we did that was different? Marlon. Okay, and that's actually really important detail the way she said that. I love how she said that. She says, we use the dashes when they're not part of the solution. If we can break it down really easily though, Raisa, what is it that we will see when we know that the line is not part of the solution? What symbols? Which inequality symbols? You said this earlier today, so I know you can do this. Yeah, the one that don't have the equal sign. So, greater than or less than is a dashed line because the line isn't part of the solution. And for greater than or equal to or less than or equal to, we use a solid line because the line is part of the solution. Okay? So that's the first thing that's different. What's the second thing that's different? And definitely much more noticeable when you look at the graph. Juan. Yeah, you shade in a side. So you have to pick a point. Not on the line. And plug it in. And plug it in. Plug it in. To decide which side to shade. Pick a point not on the line and plug it in to decide which side to shade. That's it. Those are really our 2 key points. You can keep those in your head as long as having this understanding that Raisa has about what's part of the solution and what's not part of the solution, you'll have walked away with everything that you need to know today. Now, let's do a of how this works. So the first thing that we're going to do is we're going to take the inequality. We're going to graph it just like it's an equation. So Malcolm, if I look at this inequality, what is the slope of this inequality? And Brian, what is the y-intercept? Madeline, help him out. 0, 0, because we have a hidden plus 0 sitting on over here. So the unfortunate thing about this being our y-intercept is that means that we can't choose 0, 0 as our point to plug in. Why would I want to choose 0, 0 every other time when I could? What's so great about 0, 0? Javier? Yeah, it's super easy to work with. But I can't choose it in this case because it's on the line. So I'm going to choose the next best thing. 1, 1. Actually, 1, 0 might be the next best thing. Whatever. I like 1, 1. 1 is less than negative 3 halves times 1. And that gives me 1 is less than negative 3 halves. Kip yes or Kip no? 1 is less than negative 3 halves. Everybody, Kip yes or Kip no? 1 is less than negative 3 halves. No. So that tells me not only is this point not part of the solution, that tells me everything on that side is not part of the solution, and that everything on the other side is part of the solution. So I'm shading the opposite side. Ooh, good question. So Manuel has caught me missing one important detail. What detail did I miss when I was graphing my line to begin with? Sarah? It should be a dotted line. This clearly doesn't have the or equal to portion, so this should be a dotted line. So I have to go back and fix that. Okay, not really a good, oh wait, maybe I know a way to fix it. Shh, it's cheating, I know. All right, dotted line now, good. Okay, good catch. All right, so let's look at the next one. Yes?
So the open one is the one that is not part of the problem. So it's the side that you give it to.
So the reason we chose we chose this point over here, we chose 1, 1, and we plugged that point in right here, 1, 1, to our original inequality, and we got that 1 was less than negative 3 halves. That told us that that point right here was not part of the solution. And remember, if something on one side is not part of the solution, then everything on that side is not part of the solution. So because this wasn't part of the solution, that meant we knew we weren't shading in this side, that it had to be the other side. Okay? So we looked at this down here that we plugged in. Let's look at one more example. All right, y is greater than or equal to 2x minus 3. I'll do a quick leaf change switch there. And what is my slope here? Raisa? And my y-intercept, Janelli? Zero, negative 3. So I'm going to graph 0, negative 3, rise 2, run 1, rise 2, run 1. And this time I'm going to think more carefully before I start to graph. Should this be dashed or should this be solid, Julia? Solid, because it has the or equal to portion. Okay, now I need to pick a point to help determine which side I should be shading on. Which side, what point do you think I'm going to choose? 0, 0, because I can. It's not on the line. 0 is the best number ever, or lack of number, as the case may be. 0 is greater than or equal to 0 plus negative 3. 0 is less than or equal to, or is greater than or equal to negative 3. Kip yes or Kip no. 0 is greater than or equal to negative 3. Kip yes or Kip no. 0 is greater than or equal to negative 3. Okay, so that means that this side is the correct side. So I'm going to shade it in. Kendrick, are you clear why I shaded in this side?